Hi, today I'm going to talk about my computational study of 2D conductive MOFs electronics properties. Inorganic framework is a class of porous material with high surface area composed of inorganic node and organic linker in a crystal lattice form. Due to its unique architecture, MOF has shown to be a great candidate for applications such as gas storage, electronic catalyst, energy storage, chemical sensing. MOFs are like fancy salts. As binding nature between metal and organic linker being ionic, electronically conductive MOFs required for energy-related applications remain unexplored and desirable, while most MOFs are insulators. Among MOFs, MX4-type MOF, nickel hexaminotriphenylene, what we will later call nickel HITP, has shown conductivity of 40 Siemens per centimeter due to its pi stacking along the C direction of its organic linker. With the interest of expanding connectivity along AB direction for nickel HITP, nickel HITP derivative, nickel Tetraaza annulene-Linked metal organic framework was synthesized, which we will later call nickel TAA-MOF. The conjugated carbon ring was thought to provide conductive route for the electron transfer along the AB direction. However, even with the three conjugated carbon resonance bridge between the linkers, conductivity dropped down to a significantly low value. Furthermore, studies show with the addition of iodine doping, oxidized nickel TAA-MOF conductivity raises to 10 to the negative 2 Siemens per centimeter. To examine charge transfer properties, band structure analysis was performed. One can view band structure as the MO diagram for solids, with the valence band being the HOMO and the conduction band being the LUMO. Band gap is the energy difference between the conduction band and the valence band. When the band gap exceeds the energy of the environment that is able to provide, the material is identified as an insulator. If electrons from the valence band are able to utilize external energy and proceed hopping towards the conduction band, the material is considered a semiconductor. For the very last, if the material has no gaps, then the material is shown with metallic properties. Before focusing on the result of the band structure, oxidation promoting charge transfer was something that was interesting for us. During formation of nickel HITP linker was deprotoned and oxidized. However, HITP linker was never oxidized during the formation of nickel TAA, as oxidation occurs on the carbon bridge truncate. With that being said, exploring the oxidated nickel HITP linker, unoxidized nickel HITP linker on nickel TAA, where nickel HITP was interested. While these data While these band structures data's accuracy needs to be further determined, Figure 1 shows TAA neutral charge monolayer band structure, showing agreement with the experimental result of being an insulator. The middle and right band structure on Figure 1 are the 1 electron and 6 electron oxidation monolayer. Result shows the 1 electron oxidated layer being metallic and a 6 electron oxidated layer being a semiconductor. Take in mind that 6 electron oxidated layer of nickel TAA has the equivalent valence as 6 electron added nickel HITP monolayer. While neutral charge nickel HITP layer shows semiconductor feature along the AV plane, the reduced nickel HITP shows metallic feature along the AV plane, which inspire interest towards N-type nickel HITP doping. In the future, bulk material electronic property and interaction between metal and linker would be my next step to explore by simulating bulk model and removing metal from the linker through computational methods. At the end, I want to thank the Pindon Material Simulation Lab and Presidential Undergraduate Research Scholar Program for the support. Without them, I wouldn't be the same person as I am today. Thank you so much for listening.